Hello friends. So in previous lecture we have studied Cauchy sequences, convergence sequences, and we have also known that complete metric space is a metric space in which every Cauchy sequence is convergent. We have proved that Ru, then your discrete metric space, Rn are complete metric spaces. In this session, we'll show that L infinity and Lp are complete metric spaces. Completeness of Lp and L infinity. So what is our L infinity? L infinity is nothing but set of bounded sequences. Set of bounded sequences. X equal to xi, I equal to 1 to infinity such that supremum of mod of xi must be less than infinity, where xi is either real number or complex number. Xi is either real number or complex number. Then L infinity is complete with respect to metric d infinity of xy defined as supremum of mod xi minus yi 1 less equal I less than infinity. We have proved that this is a metric. With respect to this, we have to show that this L infinity is complete metric space. Okay, so take some sequence, Cauchy sequence. So let xm is equal to m equal to 1 to infinity be Cauchy sequence in L infinity. In L infinity, where xm is taken to be as xm is equal to xi to the power m I equal to 1 to infinity. Okay, this is Cauchy sequence. Therefore, for given epsilon greater than 0, for given epsilon greater than 0, there exists some positive integer n naught such that, or n naught belongs to n such that d infinity of xn is less than epsilon for any mn greater equal n naught. For any mn greater equal n naught. And therefore, supremum of mod of xim minus xin 1 less equal I less than infinity is less than epsilon for any mn greater equal n naught. What this implies is for any mn greater equal n naught, and there this implies is this is 1. This implies is mod of xim minus xin is less than epsilon for any mn greater equal n naught and each for every I equal to 1 to dot dot up to infinity. Okay, what this implies, therefore xin n equal to 1 to infinity is Cauchy sequence in k is equal to set of real numbers or set of complex numbers. Now since k is complete metric space, therefore xin n equal to 1 to infinity is convergence sequence. Convergence sequence in k. That k may be set of complex number or set of real numbers. Suppose limit n tends to infinity of xin is equal to xi for every I equal to 1 to up to n. Then x is equal to x1, x2 dot dot etc. is sequence of points is sequence of points in K is equal to R or C, right? This is sequence of points claimed to show X belongs to L infinity. It lies in L infinity. That is to show supremum of mod of xi 1 less equal I less than infinity. This is less than infinity. This is less than infinity. That is our aim. So for this, what we'll do? Okay. So for this, xim xm is equal to xm is equal to xim I equal to 1 to infinity belongs to L infinity. Implies what this implies is this is bounded sequence. Okay. Summation of mod of x, supremum of mod of xim 1 less equal I less than infinity is less than infinity. Okay. This implies is supremum of xim or xim is less equal km, xim less equal km for every 1 to dot dot etc. and some km belongs to R. Some km belongs to R, right? Now mod of xi, I am taking mod of xi to be mod of xi minus xim plus xim. This xi, okay, and this is less equal mod of xi minus xim plus mod of xim. Now the xi minus xim, this must be less than epsilon. This must be less than epsilon. Is it right? Okay, this is less equal epsilon plus km for urea. Okay. And therefore supremum of mod of xi 1 less equal I less than infinity, this must be less than epsilon plus km less than infinity, and therefore x belongs to L infinity. X lies in L infinity. Okay. Now supremum of mod of xim minus xi 1 less equal I less than infinity. this must be less than infinity. Okay, this must be less than infinity because x lies in L infinity. Since xm and x belongs to L infinity, implies xm and xm minus x must belong to infinity. Since difference of two bounded sequences is bounded, difference of two bounded sequences is bounded, implies what this what I want to show, this is less than epsilon, sorry, is less equal epsilon from 1 as n tends to infinity, as n tends to infinity, for every m greater equal n naught. Is it clear? And therefore the infinity of xm x is less than epsilon for any m greater equal n naught, which implies xm m equal to 1 to infinity is convergent sequence. Is convergent sequence. Convergent sequence of sequences. Convergent sequence of sequences. Thus, every Cauchy sequence in L infinity is convergent, and therefore L infinity is complete metric space. L infinity is complete metric space. Class of bounded sequences of either real numbers or complex numbers is complete metric space with d infinity of x y is equal to supremum of mod of xi minus yi. Okay, so that is our metric defined on L infinity. On same line, we'll now discuss the completeness of LP, completeness of LP metric space. Example. What is LP for fixed P belongs to 1 infinity, close open interval, 1 infinity. What is LP set? LP set of x is equal to xn such that summation of mod of xi raised to p whole thing raised to 1 by p is less than infinity, I equal to 1 to infinity, where xi belongs to k is equal to r or c. Then LP is, show that LP is complete metric space with metric dp of xy is equal to summation of mod of xi minus yi raised to p I equal to 1 to infinity whole thing raised to 1 by p. This is our LP space. So let solution, let xm m equal to 1 to infinity be Cauchy sequence in LP, be Cauchy sequence in LP, where xm is equal to, what is xm? Xm is nothing but xim. Okay, I am taking I equal to 1 to infinity. belongs to LP. XM itself is one sequence. So this is sequence of sequences. XM is sequence of sequences. XM is element of LP. LP contains P summable sequence. P summable sequence. Sorry, here LP is nothing but just this one. This is less than infinity, right? That is definition of this. So XM is equal to this. Therefore, for given epsilon greater than 0, there exists some positive integer n naught such that dp of xm is less than epsilon for any mn greater equal n naught. Okay. This is equivalent to summation of I equal to 1 to infinity mod of xim minus xin raised to p whole thing raised to 1 by p. This is less than epsilon for m greater equal n naught. For this will give 1. Will give 1. This implies summation of I equal to 1 to infinity mod of xim minus xin to the power p is less than epsilon raised to p mn greater equal n naught. Mn greater equal n naught implies mod of xim minus xin must be less than epsilon raised to p. Okay. For any mn greater equal n naught and I equal to 1 to dot infinity implies each xi m n equal to 1 to infinity, each Cauchy sequence in k is equal to r or cu. Since k is complete, therefore xin is convergent sequence in k for every I equal to 1 to dot etc. Suppose limit n tends to infinity of xi to the power n is equal to xi for every I equal to 1 to dot etc. This belongs to k. And therefore your x is equal to x1, x2 and so on. This lies in what is our aim? Playing x belongs to LP. And dp of xmx less than epsilon or xnx, xmx, n greater equal n naught. Means xn converges to x. Now this is a sequence of numbers from k, that is real numbers or complex numbers. Which is right. Our aim is to show that it converges to this one. Now from 1, okay. Now from 1, what will get? Summation of mod of xi to the power m minus xin to the power p I equal to 1 to infinity. If I take this power, then it must be less than epsilon raised to p for every mn greater equal n naught and Okay, we are getting this. So as n tending to infinity, as n tends to infinity, this xi n, it converges to xi, and therefore summation of I equal to 1 to infinity mod of xi to the power m minus xi raised to p. This must be less equal epsilon raised to p for any m greater equal n naught. For any m greater equal n naught, from this is say 2, from 2. Limit of xin is x, is it right? So we are getting this one. Or here, if I take fixed k equal to 1 to infinity, k is fixed. I am taking k to be fixed. So as k tending to infinity also. Okay. Therefore, for k tends to infinity, summation of I equal to 1 to infinity mod of xi to the power m minus xi p. This is also less equal epsilon raised to p m greater equal n naught. M greater equal n naught. Okay. So I am getting this now. This is now say 3. This is 3. And this is less than infinity. This is less than infinity. What this implies? This implies your xm minus x. Okay. This implies xm minus x must belongs to LP. Must belongs to LP. Therefore, minus of xm minus x is equal to x minus xm belongs to LP. And therefore, addition of two sequences in LP is again in LP. Therefore, x is equal to x minus xm plus xm must belongs to LP. Must belongs to LP. Is it right? So it lies in LP now. Okay. Now this is say 3. From 3, we get summation of I equal to 1 to infinity xim minus xi to the power p whole thing raised to 1 by p. This is less equal epsilon for m greater equal n naught. Okay. And this implies therefore dp of xm x is less equal epsilon for m greater equal n naught. And therefore limit of xm is equal to x belongs to LP. Thus we proved, every Cauchy sequence in LP, is convergent. Therefore, LP is complete metric space. LP is complete metric space. LP is complete metric space. Now I am giving 2 examples as exercise. So let x1 is equal to 0.1, x2 is equal to 0.101, x3 is equal to 0.101001, x4 is equal to 0.101001, 301 and so on. So that xn n is equal to 1 to infinity is Cauchy sequence in Q, but not convergent, in Q, set of rational numbers. Okay. So for this, we can observe x1 is 0.1, that is 1 by 10. This is 101 by 1000. This is this upon 10 raised to 6. This number upon 10 raised to 10 and so on. So that numbers are in P by Q form, where that number lies between, in fact, 0 and 0.11 only. That number lies between 0 and 0.11. And each of xi is rational number. So this is the sequence of rational numbers. This is sequence of rational number. Therefore, this must be sequence of real numbers also. And you can observe this sequence of rational number goes on increasing. This sequence of rational number goes on increasing. As this sequence goes on increasing, therefore, and all terms are less equal 0.11 or you can say 0.1. All terms of this sequence are less than 1. So this sequence is increasing and bounded above by 1. We know that every increasing bounded above sequence is convergent sequence in RU. So this sequence must be convergent in RU. So if the given sequence is convergent in metric space XD and Y subspace of it, and that each term of that sequence is from only Y, then that sequence must be Cauchy in that subspace. And that's why this sequence must be Cauchy in QU. Why it is not convergent? In QU? If you observe as n tending to infinity, firstly I am taking 0.1, then I am inserting 1 0, then I am inserting 2 zeros, then 3 zeros, then 4 zeros, then 5 zeros and so on. Means as n tending to infinity, your xn has a decimal expansion, whose digits are non-terminating, and then if I express the real number in decimal expansion form, in which your digit after decimal points are non-terminating sequence of digits, then it is always irrational number. That xn must approaches towards irrational number. As this sequence is increasing, so as limit n tending to infinity, what xn will get, it must be irrational number. So limit of this sequence is never rational number. Is it clear? And that's why this sequence has limit in set of irrational number and it is sequence of rational number. So as it is increasing bounded above sequence in RU, therefore it is convergent. Every convergent sequence, if has all points in its subspace, then that sequence must be Cauchy in its subspace, but its limit lies in superspace RU, and therefore it must not be convergent there. Okay, this is the explanation about this. Next example, let x1 is equal to 1, xn plus 1 is equal to 1 upon xn plus xn by 2 for every n greater or equal to 1. So that 1 x2n. Okay, firstly try to show that x1 is less than x2, x1 less than x2. Then if I take x3, x3 less than x2, x4 less than x3, x4 less than, sorry, x3 less than x4, okay, and so on. Second, x2n minus 1 is increasing sequence, increasing bounded above sequence, bounded above. Third, x2n is decreasing bounded below and hence convergent, decreasing bounded below and hence convergent. Fourth part, limit of x2n is equal to limit of x2n is equal to limit of x2n minus 1 is equal to L implies this limit of xn is equal to L is equal to root 2. 5. Xn is sequence of points, elements in Q. This belongs to Ru. Okay. 6. Xn is Cauchy in Q but not convergent in Q. Implies Q is incomplete. You can construct so many sequence of rational numbers which are convergent, which are Cauchy but not convergent, and that's why set of rational numbers is incomplete metric space. So as these examples are given in exercises of P.K. Jain metric space book. So I am giving that examples as exercise, and you have to use concept from real sequence chapter from real analysis course to solve these examples. Okay, so with this discussion we'll stop our lecture here. Thanks for listening lecture carefully. Bye bye.